Okay, so let's come back to our lecture. Okay, so we've been talking about like first order equations. Okay, so just a moment. Right, so we've been talking about like first order equations. So we've been talking about like first order equations, and so that's kind of they can be linear or nonlinear. Okay, so if they are linear, it is kind of form y prime plus pt of y is equal to q of t, right? So that's a linear form, and the solution method is integrating factors, right? So the solution method is integrating factors, right? Solution method is integrating factors, and it can be nonlinear. Okay, so it can be a nonlinear equation. If it is a nonlinear equation, it takes the form dy over dt is equal to m of x of n of y, right? So that's let me do dy over dx. Okay, so right, so and this is what we call it separation of variables. Right, so that's what we call it separation of variables. So you have like two methods to work on this first order equations, and based on the scenario, you have to choose the appropriate one for your specific problem. Okay, for your specific problem. Now, for today's lecture, we're going to first talk about some kind of theory. Okay, so some theory of first order equations. So what does mean theory? Okay, so by theory, it really means like, for example, is the solution unique, right? So that's the theory amounts to such questions that we are concerned about some more fundamental issues of first order ordinary differential equations. Okay, what are these fundamental issues? For example, when does a solution exist, right? You don't know. When is the solution going to exist? When is it unique? So by this, it means that you're going to have a solution, right? So exist. So let me say exist means that have a solution. At least I want a solution. So that means exist. Now it means unique. Unique, it means that just one solution. Right? So there's existence and uniqueness, right? So exist means that you want to have a solution, and unique, it means that there is just one solution. So that's kind of existence and uniqueness issues. This is not really settled, right? Some people ask, why do we need uniqueness? Maybe, right? So some people may ask, why do you want uniqueness? Well, uniqueness, we will soon see that, of course, the existence is easy to understand, right? So it is natural and easy to understand that you want solution to exist, because if the solution even does not exist, it makes no sense to consider anything, right? So so the solution has to exist. So that's kind of the one thing that is important, definitely important for us, right? Definitely important for us. But why do we need the solution to be unique? Well, we want the solution to be unique. You will soon see that. Well, the most naive interpretation of uniqueness is that if you don't have uniqueness, then, I mean, for example, on an exam, somebody is going to come up with one solution, another person come up with another solution, because the solution is unique and is not unique. Both are correct solutions, and they have to, both solutions have to receive the full credit for such a problem. So that's kind of weird, right? So it's kind of weird, right? So but this is not the fundamental thing. Okay, so there's even more fundamental reason why you want the solution to be unique. Okay, so we'll talk about it later. Maybe when we enter the next chapter, we will see why. Okay, so however, there is another solution. Means that can a solution be extended? Another question. What does it mean? So that means you want the largest interval on which we can define a solution. So that's kind of the third thing is about extensions. Extensions, it means that, for example, you have a solution on one interval, so that's y equal to y of t. Now you want to extend this solution to a larger solution, which preserves the piece of solutions here, but it becomes larger. So you extend it to the outside of that region. And you want to consider the solution on a much larger interval I, right? So let's say I0 and I1, right? So you want to extend your solution. So that's kind of, but when you extend your solution, you have to keep the solution as its original one on the original interval. You just want to make it the interval to be larger. That's the point. Okay, so that's kind of the thing about extensions. So that's kind of the questions that we have for the beginning of today's lecture. Okay, so to start talking about all these things, let us consider the following initial value problem. Okay, so that's a very nice example that we might need to take care of. Okay, so this one says ty prime plus 2y is equal to 4t squared, where y1 is equal to 2. Okay, so this is a nice example. Okay, so the example says t. Okay, so t multiplied by y prime plus 2y is equal to 4t squared. Okay, so with the initial conditions, y of 1 is equal to 2. Y of 1 is equal to 2, right? So that's kind of a nice example that we like to talk about is the solutions. Okay, talk about the solution. So how are we going to work on that example? Well, first of all, as I said, we've been talking about first order equations, right? So can you tell me the order of this equation? Can anybody tell me the order of this equation? You can unmute. Can you repeat?
First order.
First order equation. Okay, so that's kind of very nice. I mean, and this kind of nice answer. Okay, so it's correct. And anybody can tell me, is it linear or nonlinear equation? Is this a linear or nonlinear equation?
It's a non-linear.
Somebody says nonlinear. Any other idea? Any other idea? So, so if you want to determine if an equation is linear or nonlinear, you have to first look at the coefficients, right? So what's the coefficient in front of y prime? It's t. What's the coefficient in front of y? Is 2. And this one is independent of y. So have you ever seen y squared or y prime squared? Not. So this is actually a linear equation. It's a good but I mean, it's natural to you make it's completely fine that you start to make mistakes for linear or nonlinear equations. This is very natural, and I've been seeing this phenomenon for years that people beginners are going to have a hard time. Okay, so beginners are going to have a hard time understanding if an equation is linear or nonlinear, but you have to practice. Okay, so the good advantage for such our semester is that we have a pretty nice series of lecture videos from which you can retrace what we have been talking about in our class. So this is really a first order. Okay, so first order linear equation. Is it homogeneous or non-homogeneous? Anybody can give me the answer? Is it homogeneous or non-homogeneous? Anybody has the answer? Is this a homogeneous or non-homogeneous equation? Anyone can answer me? Is it homogeneous or non-homogeneous equation? Anybody? What does it mean homogeneous? Linear homogeneous means that the term that does not involve any of the y's has to be 0. If this term is non-zero, this is first order linear non-homogeneous equation. Right? So that's the first order linear non-homogeneous equation. So this is a linear non-homogeneous equation. How do we solve linear equations? Well, for linear equations, the right idea is to use integrating factors. We just talked about that on Wednesday's class, right? So Integrating factor. What does it mean integrating factor? You have to say that y prime plus 2 over t of y is equal to 4 times t. This is what we call it the standard form. Right? So as long as the equation is in a standard form, you can try to calculate mu of t is equal to e to the power of the integral 2 over t dt. This is what we call it the integrating factor. Right? That's what we call integrating factor. And this is equal to e to the power of 2 logarithm of t. So that's going to be t squared. So that's kind of what we say by integrating factor. This is just we discussed in our Wednesday's lecture, right? So you have to go this integrating factor first, right? Integrating factor. Now, as long as you have this integrating factor, we're going to see that you want to calculate d by dt of y multiplied by t squared, because you want to multiply the y by the integrating factor, and therefore this is actually equal to t squared y prime plus 2t of y. So that's going to be t squared multiplied by y prime plus 2 over t of y. What's that? Well, y squared plus 2 over t of y is 4t. That's a 4t cubed. Is that good for everybody? Right, so then you want to get a solution, right? So how do you find a solution there? Well, there are two ways to find a solution. So if we know that t squared y derivative is equal to 4t cubed, suppose we know that, then we're going to see that t squared y is equal to t to the power of 4 plus constant. Right, and you want to determine the constant. Well, that means you just use y1 equal to 2. So that means y1 is equal to 2, which means that 1 squared multiplied by y1 is equal to 1 to the power of 4 plus c, because you set t, so it means you set t equal to 1. So that's it, right? So this is going to tell you that 2 is equal to 1 plus c, so c is equal to 1. So that means specific solution, right? So we've been talking about specific. So this is the general solution, right? So this is general solution. Specific solution is going to be something different, right? So the specific solution is going to tell you that y of t is equal to t squared plus 1 over t squared. So that's what happens to this problem, right? So that's a solution, right? So that you get a solution. Now you can see that this y1 is 2. So that means that if you set t to be a positive number, time t has to be greater or equal to 1. So that's a solution. Okay, so that's a solution of this problem, right? So the solution of this problem, right? So that's a solution. However, let's look at the statement of this problem. As I said many times in class, that you have to look at the statement of the problem carefully before you can really do anything, right? So this is a very important tip. If you don't look at the problem carefully, then you're going to run into a trouble because you might be going in the wrong direction even, right? So you have to keep yourself going in the right direction of the problem. So this problem says that it doesn't say solve this initial value problem. It just says what's the largest interval such that the equation has a unique solution, right? So what's the largest interval that this equation has a unique solution? So what does it mean? Well, let's look at the graph of this function. Okay, so graph of, let's say, y of t, right? So what's the graph of this function? Well, the function is going to look like this is t, and this is y of t. So at t equal to 1, this is going to be, so the function is going to be minimum at t equal to 1, so something like this. And it is going to be minimum at t equal to minus 1, so it's going to be something like this. Right, so I need to have a better picture of this. So, right, so I need to have a better picture for it. Right, so it's t equal to minus 1, the picture has to be something like this. So that's kind of a typical situation. Okay, so typical situation for this while of t. So that means that, for example, it says that can you find, so what's the exact question? Can you find the largest interval that equation has a unique solution, right? So how do we find the largest interval? Well, for example, the interval can be, I mean, it has to contain 1 because you start from 1. There's a y0 being restricted here. So you must start from 1. But if you start from 1, you're going to the right. How long can you go until the solution is unique? Anybody can tell me? If I start from point 1, I continue this solution, to which point the solution is going to be non-unique? Is there any point to be non-unique? No, right? So from 1 to the right, how much can you go? Can anybody answer me this question? How much? Anyone? From 1 to the right.
Infinite?
Infinity, right? So I like your answer. It's you can go to infinity. It doesn't quite matter, right? So you can extend no matter where you want. It never breaks up. But if you from 1 to the left, how much can you go? Are you going to minus infinity? Anybody has answer? From point 1 going to the left, in order to have a unique solution, are you going to minus infinity? Are you going to have any problems at point 0? Anybody can answer? From 1 to the left, how much can you go? How far can you go? Anyone has an idea? You can go at most to 0, right? Don't be shy, I mean, for answering any questions. Even if you made mistakes, it's completely fine. You're strongly encouraged to participate in the class. Okay, so that's my tip. Okay, so from 1, you can actually go much to the 0. That's the most far you can go, because at point 0, your solution is going to blow up. And if it blows up, you will have nothing, right? So that's at most you can go to 0. So that's the situation, is that the largest interval containing a unique solution is 0 to infinity. So you simply have to avoid infinities in order to avoid any possible mistakes, right? So avoid zeros in order to avoid any possible singularity. So the answer to the question that we've been posing here is just going to say that we are going to avoid 0. So the largest interval is 0 to infinity. Okay, so that's the largest interval is 0 to infinity. Okay. Now, let me ask you, why is this the case? Why is this the case? Is there any idea why this is the case? So by why this is the case, somebody is going to tell me, well, it's because you solve the equation and you don't see 0. I mean, you see the problem at 0. That's why it's a problem, right? So that's kind of this is a naive and simple-minded answer to this question, right? So naive and simple-minded answer to the question. But is it really the case? Well, not really exactly so. Why? Because your standard form. So that's very important. So if you found this equation, you didn't see any problem at point 0. So it is going to tell you that the solution is going to have a be problematic at point 0. But from this solution, it doesn't really tell you where's the problem at point 0, right? So, but once you turn the equation in standard form, right? So that's very, very important. As long as you turn the equation in standard form, you're going to have to see the problem. Why? Because if the equation is standard form, then one of the coefficients is going to be singular at point 0. And from there, you exactly know that the solution is going to be singular at point 0. So without, I mean, what I'm saying that even without solving this equation, even without any attempt to solve this equation, you are going to know that the problem is going to happen at point 0, simply because the solution has a singularity at point 0. Simply because the coefficient in front of the y's, I mean, one of the coefficients is going to have a problem at point 0, but you have to turn the equation in standard form first. The equation has to be in a standard form before you determine whether or not these coefficients are singular or regular, right? So that's the kind of problem. So that's kind of the scene, okay? So that's kind of a nice theorem, okay? So from this observation, we're going to have a very nice theorem regarding the first order equations. Okay, so let's say general fact. Let's say general fact. Okay, so we're going to have a general fact. Okay, so general fact regarding first order equation is that if you have turned this equation in standard form, okay, so if you have turned this equation in standard, so that means y prime plus pt of y is equal to q of t, then unique solution. Okay, so in order to have, okay, so in order to have unique solution, in order to have unique solution, we just want pt and qt. That means both the coefficients, when the equation is turned in the standard form, to be continuous. So that's important. The pt and qt has to be continuous. So this is like what we have been seeing here. Okay, so the theorem says that if the functions p and g, or g is my q, right? So let's say this is g of t. Okay, so are continuous on an open interval, then there exists a unique function that satisfies this differential equation with the prescribed initial condition. So the exact theorem says that if the function p and g are continuous on an open interval I, where I is from alpha, t is from alpha to beta in I, containing the point t equal to t0 is the initial point, then there exists a unique function y is equal to phi of t that satisfies the differential equation y prime plus pty is equal to g of t for each t belonging to I. And that also satisfies the initial condition that y of t0 is equal to y of 0. Okay, so that's it. Where y0 is an arbitrary initial value. Okay, y0 is arbitrary initial value. So that's kind of very important theorem. It just says that, first of all, you must turn, okay, this is very important, that the equation has to be turned in a standard form, right? So by standard form, it means the leading coefficient in front of the highest derivative is 1. As long as the equation in the standard form, in order to have a unique solution, it suffices that all the parameters, all the coefficients of this standard form equation has to be continuous. If they are continuous, you're completely fine to have a unique solution. If not, then you have to stop your interval at that point. Okay, so that's kind of a very nice theorem regarding this uniqueness of first order equations. And this is actually can answer this question, short answer. So that's a short answer, right? So in short, we can answer our previous question. It says that y prime, okay, so plus 2 over t of y is equal to 4t squared. This is the standard form, and therefore you want t not equal to 0 in order to avoid any, discontinuous points, right? So in order to have a unique solution, t is not 0, but t is greater or equal than 1. So that combined together is going to tell you that interval is from 0 to infinity, because you just don't want to jump over 0. So that's a short answer to this question, right? So that's a short answer to this question. Okay, so that's kind of what we say about the general fact regarding the first order equation. Okay, so this is about a theory, a nice theory on the solution, how the solution is being continuous, unique on a certain interval. It just suffices to justify that in a standard form, the coefficients of this equation have to be unique. Okay, so the solution can be simple in the sense that you put the equation in standard form, and then you say the function 2 over t is not continuous at t equal to 0. Therefore, you have to avoid t equal to 0, but you want to include point t equal to 1, so that interval must be from 0 to infinity. That's it. Okay, 0 must be from 0 to infinity, and that's the answer. Okay, so that's kind of a nice way to interpret this problem. Okay, so this problem. Okay, so now let me come back to the next. So far we have already finished. Okay, so far at this point we have already finished our chapter on first order equations. Okay, so we started from the introduction, and then we talked about first order ordinary differential equation. Like we have finished the theory on the solution theory for first order equation. But we're going to come to some applications. Okay, so we're going to come to some applications of ODEs. Okay, so and this is actually why. Okay, so this is actually why the ordinary differential equation is kind of a comprehensive, so compulsive class for all engineer students at our university. Okay, so we're even running this course, I mean, multiple sections. Why is that the case? Because we're not just like play fun with you, right? We just want to play, put more demanding courses on your syllabus, right? So it's not the case. It is because for every engineer, okay, so we are going to work on some practical problems in your labs, right? So, or in your experiments, you're in either your mechanical engineering or maybe electrical engineering, right? So no matter what kind of engineering you do, you must face the applications of differential equation. That means the physical process that you model in your lab is modeled by a certain differential equation. And remember, if we have the theory for differential equation, we know how to solve it, then we can use that differential equation to predict future events, right? So we can use that differential equation to predict future events. And that's kind of the really nice thing for differential equations, right? So you want to use that differential equation and you want to predict your future events. So that's the application. But the application of differential equation is not just restricted to solving it. Okay, so if you are given a differential equation, you know how to solve this equation, that's not an application. And that's not the whole thing about application, but rather applications involve something much more. Okay, so it involves the so-called modeling. Okay, so it involves the so-called modeling, right? So the modeling will be a crucial thing when you apply any kind of method related to differential equations. Okay, so what's modeling? Well, modeling means that you are going to have, so that means that physical, okay, so a physical or real world problem, okay, so real problem is going to be modeled by rate. That you're going to find the word rate in your problem. As long as you have rate, you want to say that it is modeled by a differential equation. So that's kind of the thing about the modeling of differential equations. Okay, so about thing of modeling of differential equations. So I would like to show you such a nice physical problem, right? So that's it was from one of the previous year's exams, but we're going to use that to illustrate how we're going to do modeling of differential equations. Okay, so the problem says that you have a 1,000 gallon tank, right? So a 1,000 gallon tank originally holds 300 gallons of water solution containing 100 pounds of salt. Then water containing 2 pounds of salt per gallon is poured into the tank at a rate of 5 gallons per minute. And the well-stirred mixture is allowed to leave the tank at a rate of 3 gallons per minute. Okay, at the rate of 3 gallons per minute. The first question is going to ask, how long will it take before the tank begins to overflow? Okay, so, and the second question says, can you set up but do not solve an initial value problem that models the amount of salt in the tank at all times prior to the moment when the tank overflows? Okay, so that's kind of two very nice questions that we might need to answer for this question. So how do we model it? Well, he says that you have a 1,000 gallon tank, which originally holds 300 gallons of water solution. So that means, okay, so that means, so let me say this example. Okay, so that means you want to draw a picture, right? So let's say this is 1,000 gallon tank. At first it was holding, right? So it was holding 300 gallons of water solution, right? So let's say, let me draw this picture better. Okay, so it was first initially it was holding, right? So it was holding 300 gallons of water solution, right? Water, pure water, just water. Okay, so let me draw it like this. Okay, so right, so this is 300 gallons of pure water, right? So pure water. Then it says that it contains, okay, so that's, it's not exactly pure water. Okay, so I apologize for that. It's a water solution containing 100 pounds of salt, right? So this is a water solution containing 100 pounds of salt. So that means there is salt in the water, right? So there is salt in the water. So that's 300 gallons of water solution with 100 pounds of salt, right? So that's kind of the problem, right? So then it says that if there is a pouring into the water containing 2 pounds of salt per gallon is poured into the tank at a rate of 5 gallons per minute. So that water is flowing into 5 gallons per minute and 2 pounds per gallon, right? So that's the concentration of salt in the water. Okay, so that's 5 gallons per minute, 2 pounds per gallon, right? So well-stirred mixture is allowed to leave the tank at a rate of 3 gallons per minute. So well-stirred mixture is leaving the tank at 3 gallons per minute, right? So that's kind of the, you draw this picture of this problem. I would suggest everybody to do that on your exam. Okay, so when you draw a picture, it will help the grader a lot to help them to understand what's the what you mean by understanding the problem. Okay, so that's good sign. Okay, so let's say that how long it will take before the tank begins to overflow. So that's a quite naive, simple-minded question, because if you use the volume Vt to be the amount of water, right? So amount of water at time t, then you're going to see that V0 is equal to 300. And Vt, how does Vt grow? Well, there are 5 gallons per minute into it and 3 gallons per minute outside of it. So that V of t is just the V of 0 plus 5 gallons into it minus 3 gallons out of it and multiply by the time. If you measure the time in minutes, so let's say you measure time in minutes. So that's kind of nothing but 300 plus 2 times t. That's the answer. Is that good, right? So that's kind of the simple-minded answer. So then they ask you, okay, so question says, how long, all right? So how long? Well, how long? Well, you want to say there's a T maximum is such a time that V of T maximum is going to be the maximum amount of capacity of your tank. So that means 300 plus 2 times T is equal to 1,000. So that means T is equal to 350 minutes. And that's very easy answer to this first question, right? So part 1. Okay, so problem 1. Now, what about problem 2? Well, problem 2 is more sophisticated. It says that can you set up but do not solve an initial value problem that models the amount of salt in the tank at all times prior to the moment when the tank overflows. So this is a very typical way they're going to formulate the problems for you on the exams. Okay, so that's a very typical way they're going to formulate such problems on your exams. Is that they're going to say set up the question but don't solve it. Okay, so do not attempt to do anything that's not required, because remember the exams of this class has a fixed time frame. So you have to solve your questions within that time frame. And if you don't, you will lose points automatically, right? So that's by losing points means that you don't finish some of those problems, and that's unfortunately you have to submit your paperwork, right? So that's kind of the problem with the looking at, as I said, looking at the problem carefully. Okay, so always look at the problem carefully and understand what it is asking for, because if you don't know what it's asking for, you're pointing to no direction. Maybe it doesn't ask you to solve this equation. They just explicitly said, don't solve it, right? So in my previous years teaching of this course, I do see people solving those unnecessary equations. I mean, they don't, we said you don't need to solve it, but why you solve it? So they run into problems for this, right? You run into problems. So do not solve it, right? So you just set up this equation, but you want to model the amount of salt at time t, right? So what's the amount of salt at time t? I say if qt is the amount of salt at time t in the solution, let's say qt is the amount of salt at time t, then how do we model this problem? Well, we're going to use a very basic and important principle that applies to almost all the questions in this semester, okay, in this course, is that if you have certain amount in the tank at time t, then we are going to have this rate change of q. Let's say rate change. That means how much Q changes per unit time. The rate change of Q is the inflow rate of the change of Q minus the outflow rate of the change of Q. That's very easy to understand because that means the inflow changes the Q at certain rate, the outflow changes the Q at certain rate, their error is going to be the net rate change of the amount Q. So that will help you to build a differential equation because you are always able to say that the net change is dq by dt. You just want to understand the inflow rate and the outflow rate, right? So, but remember, the inflow rate is not the inflow. Is it the inflow of fluid? It's not the inflow of fluid because it's the inflow of the amount of salt per unit time. How much amount of salt enters? But in order to consider the inflow rate, you really have to understand that the inflow rate is actually the inflow fluid rate. By inflow fluid rate, it means per unit time the volume multiplied by the inflow concentration. Concentration means that how much salt in the per volume. So that's a product of inflow rate multiplied by inflow concentration. Same thing for outflow rate and outflow concentration. Right, so that's kind of going to tell you that this inflow concentration is the inflow. What's the inflow fluid rate? Inflow fluid rate is 5 gallons per minute. That's the amount of fluid. And 2 pounds per gallon, so that's going to be 5 multiplied by 2. Minus the outflow rate. Outflow rate is 3 gallons per minute in terms of water solution. But what's the concentration? We know the inflow concentration is 2 pounds per gallon. That's clear. But what's the outflow concentration? It's not clear at all because it didn't tell you what's the outflow concentration. So what's the problem? Well, let's look at the statement of the problem. Statement of problem says that you set up this equation, but do not solve this equation. But then it says that well-stirred mixture is allowed to leave the tank. What does it mean, well-stirred? Well, well-stirred mixture, it simply means that the solution of this salt, right, the water solution of the salt is homogeneous. So the salt is kind of equally distributed, or we say it is kind of homogeneously distributed among this water solution, which means that the concentration can be calculated, right? So what's the concentration? Concentration is the amount of salt at time t inside the tank divided by the volume of the tank at time t. That will be the concentration, right? But what's the volume? Well, volume is 300 plus 2t. So you're going to have this equation, dq by dt is equal to 10 minus 3q divided by 300 plus 2t. That will be your equation where q of 0, right, the initial amount of salt is 100 pounds, right? So that's 100 pounds, right? So let's say maybe you don't need even need, as long as you have unified unit measurement, you don't need that pounds. It's going to be just 100. So that's kind of going to be your initial value problem. Remember, the problem says that you have to set not just a differential equation, you have to set an initial value problem. So that's, it has to be an initial value problem, right? So that's kind of what we say for such an initial value problem, right? So that's kind of what we say for such an initial value problem, right? So, okay, so that's kind of the initial value problem that we really see. So important thing is that once you have this notion of well-stirred mixture, it implies that outflow concentration is the quantity of the salt at time t divided by the volume of the water at time t, which will be the concentration. So that's kind of a nice way to present such a concentration. Okay, so that's kind of a nice way to present such a concentration. Okay, so that's all we have for this lecture. Okay, so that's all we have for this lecture. We're going to stop this lecture a little bit early, and we're going to come back to it. Okay, so come back to it sometime later. Okay, so in the next lecture. Okay, so let me. So we're going to let's finish today's lecture at this moment, and let's come back. Okay, so let's come back to our next lecture, and we're going to continue with this investigation. Okay, so see you on the next lecture.